All right, we'll give it just another minute in case anybody else jumps online.
You should simulate and show how it could be stabler.
Simulate which? Oh, just the economies. Steven, do you want to mention that paper you found about simulating economies with like a Unity type environment? Just real quick, Misha was mentioning something that just before we get the class started. Before.
Let me see if I can turn on video real quick. Okay, cool. So there's a paper. I don't remember the authors or where they're from, but they were economists, and what they did was they said there's a bunch of different economic systems, and all of them have benefits, and all of them have downsides. Those are in terms of like equality in the economy, how much is everyone producing. Like you could solve unemployment if you really cared about unemployment by making everybody who is unemployed a slave or by killing them or something, but that's not what you want to do. So what this paper did is it used a simulated world like Unity, but it was a game, and in the game it's kind of like Minecraft where you can walk around and harvest stuff, and then you can exchange materials for goods, and then you can, if you're like a higher skilled person, you can then create new things, build them, harvest more things. And what they tried to do was figure out, like what type of economic system could we have if we cared about.
You're breaking up from here. Sorry, you're breaking up.
And create an economic policy.
We can't hear you.
Hello?
Just tell them in the mic.
Hey, we can't hear you. You're breaking up.
Ah.
We lost like the last 30 seconds.
What did you last hear rather than 30 seconds?
Right after Minecraft.
Cared about.
Okay. Am I audible now or no?
Yeah, you're good.
So it's like Minecraft. You can gather supplies, and then you can either just sell supplies, or you can purchase supplies from someone to manufacture more complex goods that other people need. So think of it like the lithium miner versus the person producing the iPhone. They require different amounts of skill, different amounts of time. Anyway, if you simulate like under some distribution of like who's going to have like a 99th percentile IQ or something like that, who's going to be able to produce things, what they found is that you can have people who want to earn more money and be productive, so they're willing to work harder to like create new things, but without having people at like the bottom like lose all of their income and like not be able to survive in society. Anyway, they showed under a number of measures that economists will use, like GDP, production, stuff like that, that you can have a different economic system by changing tax rates. It was really cool, and I'll post a link to the video.
By changing what? By changing taxes. Oh, by changing taxation systems?
Yep.
All right, thank you, Steven. Yeah, so let's definitely, try to simulate that kind of stuff. I think that's super cool. All right, looks like we've got just a couple more people jumping on. Let's give it one more minute.
And I also just put a plug out there. If you're not following 2-minute papers and you're interested in the material in the class, you should really reconsider following 2-minute papers.
Is anyone talking? I can't hear anything.
I don't believe so.
All right, never mind.
It looks like Professor Han is talking, but
He's just talking to the room. He's not lecturing yet.
yeah.
Will wants you to know that the system is broken here.
Thanks, Matt. Of course. Amanda, do you mind if I ask you a couple questions while you're here and while we're waiting on Will to reboot?
All right, I think we're back. Can you hear me?
Can hear you.
Can.
Yes.
Great. Apologize for that. The computer completely froze up and had to restart. Okay, so last time we were looking at one of our notebooks with convolution. Let me share the screen. Hang on. Okay, so we're going to pull up our notebook we were looking at last time. You can find the link to this off of the GitHub for the class. We're looking at this notebook, convolution and PDE, partial differential equations. So last time we were looking at this Firespire model, and then we were looking at this idea of convolution. So we're going to very quickly review this convolution idea, just scroll through that. And then we're going to look at how we can use this convolution to count. And so when we did the Firespire model, we used this idea of looking at neighbors to basically count, to see how many of our neighbors are at a certain level, and then that determines what we're going to do. And we're going to see there's just an extraordinary amount of really awesome models that you can do with that really simple paradigm. And then we'll switch over to Golly and look at some of these cellular automata models. Okay, so we had our image. We pulled these in from the web. We're just going to kind of go through this at lightning speed. Let me know if you have any questions. Just to remind ourselves, we have these little filters where we have the center square is going to be us, and then these are going to be our 8 neighbors. And we're going to decide at each time step to become a mixture of our neighbors. And with that kind of paradigm, we can do things like image processing, where we can extract certain features, in this case, a horizontal line, or in this case, a vertical edge. Now imagine if you're like a bird and you're trying to figure out if it's something you can eat, or if it's a place to make a nest, or if this is a string or a stick to build nest making material, that these kind of visual extraction would be very, very helpful in that kind of a setting. So we made this code by hand with a simple for loop. Then we compared that. We sort of ran some random filters. We compared the timing of these. Our homemade, it takes 10 seconds to run this 9 times. It takes us 7/100ths of a second to run this 9 times with the optimized code. And then when we run the graphics processing unit, right, this is like the 1990s supercomputer that we get for free in the cloud on Google. And this thing can do in 1/100th of a second, we'll do this 96 times. All right, this is extraordinary. And I think this is really about, what it means to be a mathematician in this, this new era, this new century. The traditional math is really about proof. And I was thinking this morning about we need the new expression. And I always like the expression, proof in the pudding, or the proof of the pudding is in the eating, right? And what that means is you got to it doesn't work, right? If you can't eat the pudding, then it doesn't matter. And I think being able to take math and actually, do stuff and show that it's really calculating stuff, we can dream with squiggles on a chalkboard all we want, but at the end of the day, we got to put the stuff into an actual engine that runs. Sometimes when you run this code, stuff will like change on you. So last time we ran this, we had a different picture of some fish up there. And when I ran this last night, suddenly that picture of the fish wasn't on the internet anymore. So I switched it out. So if you ever get a problem like that, you can just change this out and put in a different JPEG. So I just put that one in there. We did a random blur of that fish. So you can see it's just a random, now it's all blurry. But now that might be a good model for like what a shark, vision is like. They probably don't have high fidelity vision, but that would be good enough to chase down a fish to eat it. In fact, it might be better because then you don't have as much information to have to process. We then looked at how this convolution can find things. If we set up the filter as an object we're looking for, like this coin, and then we convolve across the image, we'll get nice bright spots where that matches, and then we can find out where those spots are and get those bright spots. Okay, so now what we're going to do is we're going to go back to this idea of this game of life, and we're going to code this from scratch. And the first thing we're going to do for that is we're going to define our convolution. And in this case, we're going to look at this filter here. Let's make this a little bigger. And what this filter says, it says, don't count me. So you kind of want to wrap this in your head. Sorry, give it a second. It's resizing. Okay. Let me run everything before this. So I'll do run before to wake up the notebook. So what we're going to do is we're going to create a random world, just like we did with the percolation. We're going to make it 100 by 100 on the side. We're going to test to see if it's greater than a half. That will be the black and white squares. And then our filter, the way we want to read this is this is the center pixel that you are, and then these are your 8 neighbors that you're going to be looking at. And what this is saying is that their weight, their importance is just 1. That you count your neighbor by a 1 if they're a pixel. So you're going to basically be weighting and counting your neighbors. So let's give this a second to wake up. And when this runs, what we're going to see is this little matrix here. Let's put in another block of code. And we'll print out F by itself. It's still running these up here, so we'll give it a second. Yeah, that's a good point. Okay, so let's look up. So there's a suggestion that we look at the difference between these two neighborhood functions. And so one of them is called the von Neumann neighborhood, and named after John von Neumann. And that just says you're only going to look at the square, sort of, you could imagine on like north, south, west, and east here. But there's another one we can have, which is going to have this more neighborhood, which is going to have the northeast, southeast, southwest, and northwest. And so typically this is the one that we're going to be using. And so now we can see we have our center pixel, and then we have the 8 neighbors. To do our counting operation, we're just going to make the weights just a 1. And then that will actually tally to see how many of the pixels around us are equal to a 1. And so let's look at that filter here by itself. Hang on, let me run this. There we go. That way it's just a little bit easier to see, kind of wrapped out like that. Now, the largest this can get is if all of your neighbors are turned on to be a 1, then it's 1 times 1 plus 1 times 1 plus 1 times 1 plus 1 times 1, blah, 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 blah. So this would be an 8. So the largest that could be is an 8, which means every one of your neighbors around you is on. And the smallest it could be is a 0, which means none of your neighbors are on. And then it'll, in general, be something in between. And so we're going to use that simple filter to run our game of life. We're going to start the world like this. We'll just start it, very full of stuff, but just randomly. Random. Okay, we're going to take 1,000 steps in this world. We're going to save everything for an animation. So we're going to create a big tensor of zeros, some empty scratch paper. It's going to be the same size as this image, 100 by 100. But then we're going to have a dimension for each one of these time slices. So you can think of this like a flip book, right? So you're going to flip through these, and you're going to have 1,000 pages in your flip book, and each page is 100 by 100. This is going to just convert it to the format of a tensor to get it used for PyTorch. So we're going to use the PyTorch program so that we can run on the GPU. We're going to tell it that we want these things to be integers. We want to count these as whole numbers. The numbers are either on or off. The squares are either on and off. And so we'll run that there. And so what this is going to do is the first step is going to count the neighbors. And so we're going to take our world, we're going to run that filter F, and that's going to give us back a number n. And now, like what I like to do when I write code like this, I have many, many, many more cells in between, and then later I'll delete them once I get the final working version. You want to take it and do it in reverse. You want to take it and sort of look at these things one at a time and say, well, what did that line actually do? And to do that, it helps to kind of print it out and see what it's actually doing. Sometimes it's hard because there's a lot of pieces. But what it's saying is, let's see. What's that?
You might have died.
Which died?
The world.
Oh, the world? Hang on, let me reset it from up here. Okay, so here we go. And so here we're saying that this neighbor had 4 that were turned on. This one had 5. This one only had 1 neighbor. This one had 2 neighbors, and so on. You guys remember the game Minesweeper? Right? It's a lot like that. It's telling you how many are around it. Coincidentally, I tried to get AI to program that like 20 years ago. I didn't know enough math. I knew enough programming, but not enough math. Yeah. It is padding, but after. So should we add the pad before?
Yeah.
Yeah.
Otherwise, that's going to happen.
So let's see. Okay, so one of the ways convolution works is, let me pull up that other website. I think we have the link right up top here. If we scroll all the way back up top, let's pull up this website again, this image kernels visually explained. So it's at the top of the notebook, the link there. And this is a good example of showing us how this operation that we're doing is not defined for the very upper left-hand corner or the very upper right-hand corner or anywhere along the edges. And the reason why is because the recipe is looking for something 1 up and 1 over, and there is no 1 up and 1 over in the top corner. So to do that, what we do is we temporarily add extra 1s or 0s along the outside, and then that will make the image a little bit bigger, because if we don't do that, then we lose a little bit along the outside of the edges. Okay, so let's jump back to here. Feel free to split this into multiple notebooks. You don't have to have this all in one big scroll. This is just so I have everything in place for for right now, but it makes it a little dizzying to look at all the stuff at once. Okay, here we are. Okay, so we have this padding. I was doing that on after, but let's see if we could try that. Well, I know it works this way. Let's do it this way, and then we'll try to switch it. So this is going to run the convolution, and then it's going to sort of replace that with ones along the outside. And then we'll switch that after. Okay, so we've got our matrix, we've got our filter. We're going to plot that. We're going to put everything on the GPU. We tested our counting neighbor function at work, so we can delete those intermediate lines now if we don't want them. So we'll do this 1,000 times. Now the key step here is this, and this is kind of a funny way of writing code, but what we're going to say is that if you were equal to 2, if you have 2 neighbors, then you stay whatever you were. So W is the state that you're in. W is either a true or false. And so I'm kind of using these logical operators and programming in parallel. And so that's what you're going to kind of get used to. Don't worry if it doesn't make sense right now. We're going to go through a lot of different examples and you'll get more practice with it. And so we're using these sort of math operations to do this programming. And so we have 2 terms. And these are logical operations. So there's a equal there. And the equal says, give me a true whenever these things are true, and give me a false whenever they're false.
When you're pointing at the screen, could you do it on the actual computer screen? Because we can't see the board.
Yes, thank you so much. Let me know. Thank you. Okay, yeah, so this term here, we have n equals 2. So that's saying which of these neighbors have exactly 2, which of these cells have exactly 2 neighbors? And so that was true for this one, for that one, and that one. We could plot that as an image as well and just look at just that piece. So this is what you want to learn to do is sort of break up and, let's see. It says, okay, so let's see. It says an invalid shape. So it has 2 extra dimensions here. And that's the reason why is because in general, we might want to use a color image and we might have more than one image. And so what we can do is we can say here with square brackets, say, well, I just want the 0th of the first index, the 0 of the first index, and then we'll put wildcard for the last 2, square bracket, and then that should print that out for us. And so what we've done here is we're saying ignore those, or go to the first 2 of those, and that will essentially index out those dimensions. Again, we can make another thing to prove that to us, and we can do dot shape to see that by doing this part, we've indexed out those first 2 ones, and now we just have 2 rows and columns. And if I have just rows and columns, then I can plot it as a picture. So these are all the locations that had exactly 2 neighbors. And so if we go and we look at the game of life rules, and so we have these rules here. So any cell with 2 or 3 neighbors survives. Any cell that has exactly 3 will become alive, or any dead cell with 3 neighbors becomes alive, and all other cells die in the next generation. So there's the sort of 2 formulations of this, right? That's sort of the simplified one. And so we're going to say, is it a 2? So if it was a 2, then that means we want it to become a 1. Okay, so when we have here, if it's going to be a 2, then that will return a 1, and then we'll multiply that 1 by whatever W was, and then that'll just stay whatever it was. Now, if we just cover up, I'm pointing in the wrong spot, yeah. So if we look at just this term will say, if you were a 3, then add 1 to this W, then you're going to add 1 no matter what you were. W is just going to be a 1 in that spot. So if you had 2 neighbors, you stay. If you had 3 neighbors, you're going to go up by 1, and otherwise it'll just not survive the round. Okay, so if we run that and then send to this program, make animation.
It's worth knowing for those who got confused by that adding 1, that those are mutually exclusive conditions.
We lost the mic.
Say again, Misha?
Sorry, your volume went down a lot.
Sorry, it's worth noting that for those who were confused by that adding 1, that since they're mutually exclusive conditions, you're actually only going to become a 1 if the case is n equals 3, or exclusively if the case is n equals 2 and the case is I am a 1.
Yeah, because if you were a 0, then this won't do anything. Okay, so we'll go through and we'll look at how to rewrite those too with if then else. But I just want to kind of dive everybody in to start thinking about this other way of programming, right? And it's a little funny at first, but I think it's really powerful with when we get into more in the deep learning stuff.
Oh, we got 5 oscillators there.
Okay, so now we've got a really cool animation. It's on a loop here. It's 10 seconds long. It's really kind of fun. You can right click this, or let's see if we, in this one, sorry, it was a little slow. There's some ellipses here. Then we can choose download.
It's right at the bottom.
Yeah, let me just click here. All right, so now you've got, something super awesome for your social media. All right, this will get tons of hits. Whatever you want to do. That's what I would do. I get tons of followers with this kind of stuff. Okay, I just think this is really awesome stuff. We're gonna go look in a second in the other program, Golly, that we looked at last time, and just see some really amazing cellular automata. I think this is a field that hardly got started. It was founded by John von Neumann back in the 50s. Let's see if we look at our GitHub. It logged me out when I signed out. Okay, let's see. Trying to think, did I upload that one? I put another PDF aside for you guys. I'm not sure if I actually uploaded it. It might still be on my desktop. Yeah, I'll upload that one this afternoon. But I found the original von Neumann paper on this, or his book on this, and it's extraordinary. So we'll come back to that. But I just couldn't believe how long this field has been around, and yet it seems to be really taking off. And I think there's some really serious science about this stuff. I love, like I said last time, the sort of pond water under the microscope look and feel of this stuff. I think it's really extraordinary. I think it's at the heart of complex systems. And what we're getting at with all this stuff, we have a mind-numbingly simple model, right? This is like a board game. You could get little kids to play this game on a small scale. You could simulate this outside, and yet we get sort of like almost unimaginable behavior. Like, where does all this stuff come from, and sort of what's happening, and truly this emergent phenomenon. What's really fantastic to remember is this is purely parallel computing. At least we're simulating a parallel computer, in that each square of this cellular automaton is doing its own thing, and it's only looking at its 8 local neighbors. It has no concept, every cell has no concept of anything beyond its 8 local neighbors. And there is no communication or no bus or no anything, no bandwidth between cells other than by their nearest neighbor. So this is purely local and purely parallel and distributed. Okay, so there's lots of other things that we can model with these systems. And don't stress about how you would have invented these formulas. We'll look at that later. A lot of these were actually kind of evolved to do stuff. But this is a really interesting that models something interesting one that models surface tension. And so if you put like a little drop of water on the table in the sun, you can sort of come back, you can watch it, disappear in real time, like on the beach if it's hot enough. And what happens about that? I think one of the classic interesting things in science that we don't really think about enough. If you drop the water on your flat table, right, it makes a mound, right? It doesn't go flat on the table. Well, we would expect gravity is pulling on all of the water molecules. Why doesn't it just make a thin layer across your table? It doesn't. It makes sort of like a little hill. And that's because of the surface tension, the forces between the molecules. And so this is a model of that. So again, we're going to start it just the same. We're going to use a similar neighborhood model, except we're going to count ourself. And so there's a 1 there in the self position. We're going to do everything exactly the same. We're going to count our neighbors. Now what we're going to do is we're going to say, if you were less than 4, or you are equal to 5, and then we have a not.
Why not just less than or equal to 5?
You want to try it?
Better yet, why not just greater than 5?
Okay, so we have a proposal for another formula. So what do you want to try?
Just greater than 5?
Just W greater than 5? Just like this?
Oh, no.
Oh, I need a W, right? Like this? That. Yeah, okay, sorry. It's so much harder when you're trying to take the somewhere else. Okay, so, all right, let's try it. And that's what's so amazing about this sort of,
No, that doesn't include 4. Never mind.
but that's what's so amazing about this sort of experimental framework is we can try stuff. So there we get something, right? And it's not quite clear what we might get with that model, but that's really, this sort of digital petri dish that you have at your disposal. And, I want to reemphasize that these classic mathematicians like von Neumann and von Turing and stuff, if they saw this, they would just push you out of the way. They'd be like, just give me the keyboard, right? They would just be unbelievably excited to have this sort of virtual universe where you can build these things. There's another paper I'll pull up. I think his name's Botticelli, I think you say it. He worked with von Neumann, and he did these sort of very early digital life experiments to try to just really create, digital life forms.
It's minus n equals 4 for that. And greater than it.
Did I mess up something?
Minus n equals 4.
Okay, let me reset this and then make sure that we go back to the beginning. So by all means, try these things. Put in different formulas. Make up formulas. I very much code on the right side of my brain. If I had to logically, deduce what's going to happen every time I hit the enter key, it would take me 10 years to program stuff. So I'm constantly being like, oh, let's try it. And the computer will very quickly tell you if something works. And I think this whole field is sort of about experimental programming, right? Writing computer programs and seeing what happens when they run, because you can't predict ahead of time. And cellular automata are sort of the quintessential case for that. You really cannot predict that. And we'll see that when we look at Wolfram's one-dimensional automata. Okay, so let's run the next one. This one's our old friend, the Firespire model. So let's just look at that one again. We have this chance of lightning. We have a chance of growth. We're going to set it randomly. We're going to do the neighborhood count. We're not going to count ourselves. We're going to load everything onto the GPU and make the storage for the animation. We want to say, so we have empty is 0, 1 is burning, 2 is a green tree. If we are a 2, then that will be a 1, and then we get multiplied by 2, so that means we will stay a 2. So if we focus on just this line here, we can think of it as sort of, if it's a fixed point if you're a 2. If you're a 2, then that means this is true, which means you get multiplied by 2, which means you went nowhere. If you were bigger than 0, then if your neighbors are bigger than 0 and you were equal to 2, then that means that you were a green tree, is this part, and one of your neighbors was on fire. And so that means that you're going to be a 1 the next round. So there's sort of an implicit 1 times here, right? And so the way this code works is sort of, this is the sort of condition, and then this will be the value that gets put into place when that condition is met. If, on the other hand, you are a green tree, and this, by chance, this thing happens to be true for the square you're on, then you're going to get caught on fire. You're going to subtract 1. You were a 2. You're going to subtract 1. That will mean that you're a 1, and that means you're on fire now. And on the other direction, if you were empty, and by some chance your square happened to grow a tree, then you're going to become a 2. And so when we run that, this is one of my favorite things. I could just watch this thing all day. Let's download it so we can see it even easier. So I'm going to hit download. Now you've got this ready for your MySpace account. No, just kidding. That's what that is. Okay, so I could just watch these things all day. Run these a few different times. You get to check this out. Change the parameters. You can start it out as a full forest too. We don't have to start it out as empty. You can start it out random like we did the other ones. You can start it out completely dense. You could put like a large swath to make the fire trails like we talked about in the Pine Barrens, New Jersey, like they dig so that the fires don't get too big. What I really love about this is it almost seems like there's something happening at a higher level though. This sort of wave front, it feels emergent, right? It feels like there's something coherent going along. This thing sort of knows it's all along the edge of a fire or something. But that's really just like in our head. That structure, well, I guess that's a philosophical thing, right?
That's literally the neighborhood.
We're seeing the neighborhood activation, right? But you get this sort of macro behavior, and I think we'll see that in a minute with the other one. Okay, so this one models what are called nonlinear waves. And so these are like the type of waves that control the beating of our heart. There's a really great website. You just type in virtual heart GPU, this will come up. And they've got some really great models in here about these types of waves, and these run really cool on the GPU right on your computer. And so we're gonna simulate those in just a second. And so go through these. This is some really cool stuff if you're interested in this type of mathematics. Looks like they changed their website here. Okay, there we go. It looks like they got a new website. Okay, so that's really cool if you want to check that out. But what this is going to do is we're going to make those ourselves. And so we can set some different values here to get different kinds of waves. We're going to set everything else just the same before. We'll do the neighborhood, not counting ourselves. And now this is going to be our rule. We're going to first set the neighborhood is only going to count if you're bigger than 0 but less than some threshold. And so we're going to count yourself as a neighbor only if you're in some sort of range between 0 and t. And then we'll do the neighborhood count. And then if we're bigger than some other threshold, if we're equal to or bigger than some other threshold t1, and we were a 0, then turn on to 1. If you are a 1, become a 2. If you're a 2, become a 3. If you're a 3, become a 4. If you're a 4, become a 5. If you're a 5, become a 6. Oh, sorry, I'm pointing and not highlighting. Right? So here, if you're a 0 and your current value of your neighborhood exceeded this threshold t1, then you turn into a 1. If you're a 1, then you turn into a 2. If you were a 2, now you'll turn into a 3, and so on down the line. And if you are a 9, then you reset and you go back to 0. So I loved dominoes as a kid, but I never really had the patience to set them all up, right? And so this is awesome because you get a million dominoes at once, and you just hit a button and set them all up. All right, so let's run that, and they stand themselves back up. All right, so here we're seeing dominoes that have sort of 10 different flavors, and then they stand themselves back up. Download that and make it easier to see. And so when we run that in the beginning, we get one effect, but then once in the second part, where it sort of annihilates itself, we get these spiral waves. So I'm sure you've all seen like the defibrillators on TV and the hospital and stuff, and they go clear and do the thing. What they're trying to do is they're trying to reset the dynamics of these on the heart. And so this is some really fascinating mathematics about that. And it shows up in a lot of other systems, and we can see there's just this very kind of simple model. So one of the things I'm trying to show you is I've tried to work really hard to get this code to be down to like sort of brutally simple, primitives. I think a lot of this type of math has been sort of locked up for so long behind very sophisticated training you'd have to go to manipulate these things when you don't have a computing machine. If you don't have a computing machine to work with these types of systems, it takes a lot of really sophisticated linguistics, so to speak, that we call advanced math. And it takes decades to learn that kind of stuff. I think now we have the opportunity to just jump right in and say, all right, now I know this is kind of cryptic and we'll rewrite this so it makes more sense. But you can see there's nothing else to this, right? You can go through and say, all right, well, there's nothing else to it behind the scenes that's happening. And yet we get this very sophisticated kind of patterns. When I went and studied this kind of stuff, I dreamed of being able to make these simulations. And when you go and you ask the math professor, you say, well, what are the equations of these dynamical systems in this type with partial differential equations? Well, you're never going to get anywhere you can actually plot them. They'll just sort of give you equations. And so I love putting these things into motion and seeing kind of how simple they are. Okay, so this next one is really one of my favorites because and I really think there's a lot of really great open research that can be done with this. So I encourage anybody who loves this kind of stuff, we can talk about some experiments we can do. This one is called Wire World. And what I think is so extraordinary about this is with these very simple rules, let's pull up those rules. So again, this one goes back to 87. And so this one has some simple rules. So the wire world cell can be one of 4 different states, usually 0 through 3. And we're going to have 0 means it's empty. And we're going to model an electron. So this is a sort of a digital physics. And the electron has 2 parts to it, right? And so the electron has a head and a tail. And then we have a conductor, which will be the wires. And we have a very simple rule. If you're empty, you stay empty. If you're an electron head in the square you're in, the next time down, you're going to be an electron tail. Think of these as colors, right? So if you're color 0, you go to color 0. If you're color blue, if you're black, you go to black. If you're blue, then you're going to go to red. If you are red, you're going to go to yellow. And if you're yellow, you go to an electron head if exactly 1 or 2 of your neighboring cells are blue. Otherwise, remain conductor. And this one uses the Moore neighborhood. So we have this extremely simple algorithm, extremely simple rule. Each square is working completely independently. And yet we're going to get sort of this emergent behavior. And so in this case, what we'll do is we'll set up the world to be this little wire. So I'll just set up, I'll set up this one here to have sort of a line in it. So I'm going to say all of the columns at row 50, make them into a 3. And that's a wire. And then at spot of row 50 and column 5, make that the electron tail. And at spot 50 and column 6, make that the electron head. So we're going to make a wire and put one of these 2 squares in there. And then when we run this, I just think this is the coolest thing in the world. It actually just makes this thing scoot along. And what we have to remember is there's no code in here that says scoot along, right? There's only these simple rules about what you should do at each square. There's no actual motion in a sense. This is like the stadium waves, right? You know, like in the soccer stadiums when people stand there, oh, and then like, there's no, people don't move, right? Only this sort of excitation of the pattern actually moves. And so this is like a little mini stadium wave, right? And the people are standing there and they say when the person, it's sort of very organized, right? Sort of a 2-person standing wave kind of thing. And what I really love about this is it allows us to go from like very, very simple math very quickly to sophisticated algorithms. We're going to look a lot about the Turing machines, and those are really fascinating, but it's hard to get them to do, you know, complicated things. This is really neat because you can quickly jump in and make like a calculator out of them in a modern sense. Okay, so let's set up another initial condition. So the exact same world. I'm just going to kind of pre-paint some of these pictures here. So I just kind of did this by hand. I said, all right, let's make these a wire. And then let's put the electron head and tail there. And so now if we run this one, these are already here, so I don't have to even run them. This is going to make us an oscillator. And so just, you know, again, there's nothing, you know, programmed about this except for the simple rules. But yet now we have this emergent behavior of something going in a circle and then kicking out copies of itself as it goes around. I just think that's so cool. Okay, so now we can do this with some other sizes. I have the wire work calculator in the other section. Yeah, we'll show that directly in Golly because it runs real fast. You know. Yeah, have you seen it?
Not in Python.
I know, it's so cool. Let me pull it up. I think it's on our GitHub too. Yeah, so there's another one on the GitHub called Wire World directly. I put this one in its own notebook. Just because this is just so cool. I mean, this is just kind of, it should be in an art museum, right? Okay, so what we have, we'll see what it looks like in a second. Hang on. Okay, so let's wake this back up. The same thing, but in another notebook. Okay, there's the one going down the line. Let's do the oscillator. Okay, now what we can do is we can load in this crazy pattern, right? So this is a picture, it's a PNG file, it's on the GitHub. And this is a pattern that just has these colors in it. It's got black squares, orange squares, white squares, and blue squares. And so we can figure out what the colors are, and we can load this into a NumPy array. And so now this is actually an array, and it's just a giant matrix, and it has this pattern in it, right? And so this pattern comes from circuit theory, essentially. We're going to look in a second at some programs like that. And what's so unbelievable is that when we run this code, because it simulates the electrons moving around, we can build the rest of logic out of that. And we can make this functioning calculator that is itself a photograph, right? Like this program, let me download this. This is a computer that's defined as a pattern. We'll go in the other program, we can zoom in on this. And very exciting, it's calculating 3 up there, and then it shows 5, right? And so you guys can probably much faster than this determine that 5 is the next prime number after 3. And so sort of what it can accomplish is not tremendously exciting, but how it does it is sort of mind-boggling. We have a machine that's defined purely as a pattern, as a photograph. And yet when we run this automata rule on that photograph, it essentially is executing that hardware. And this hardware is simulating, this is a 7-segment display, and it simulates all that kind of stuff. I think this is like the coolest thing in the world. Run this yourself just to convince yourself that it actually works. It goes slow in the Python version, even though I'm running it on GPU. If anybody has some ideas about how we could speed that up, that would be fantastic. But in the meanwhile, what we'll do is we'll switch over to Golly. And Golly is sort of jokingly called a professional cellular automata program, because I don't know who all these professional cellular automatas are, but they have to be out there somewhere. And we'll find them yet. But this is a really extraordinary program. So to remind you, we can put in a pattern here. We can hit play and just run it. If you haven't had a chance to run this yourself, don't deny yourself this fun, because it is really, really awesome. Okay, so we can go through. We were looking at some of these patterns before. We can put in a whole bunch. I wanted to take a look at a particular set of rules on here. If I can find it. Yeah, the JVN. So John von Neumann himself constructed a number of these. And so if we pull this up. So he proposed this cellular automata and this universal constructor. And so this is what we're going to look at. And this is really awesome stuff. And so here they have it represented with arrows. In our version, it's just going to be colored squares. And now he basically generalized the game of life, although this is decades before the game of life was published. Von Neumann came up with this system that's very much like the game of life, except there are 29 different states you can be in. And that sounds dizzying until you just realize they're colors, right? So rather than just being black and white, each square can be one of 29 different colors. And there's a rather complex rule about what color to switch yours in based on what your neighbors are. But it's going to use the exact same rules in the sense of you only look at your neighbors. And so here is the set of instructions. Or basically, here's all of the states that you can be in, right? So he defined it a ground state, then he had this transition or sensitized states, confluent state, ordinary transition. So don't worry about the details of this, right now. I'd encourage you to if you're interested in the research, but don't stress about it. And he basically had these rules, right? If the cell in the ground state you give it an input, it will transition, da da da. So you have these kind of rules, just like we looked at the other, that determine how you're going to convert your pattern to the next one. And so we can run that in here. Okay, and what you can do with this kind of stuff is really spectacular, in that it really simulates what's called digital life or artificial life. And so here we're going to run this pattern. Here's just some pattern. We can think of it as a genome. It's just this pattern of purples and greens. But when we run this rule, so we're going to run the cellular automata rule on this. Now we can use the plus and the minus. If I do minus sign, this will slow this down, so we can actually kind of watch stuff tick along. Or I can press plus sign and really speed this up. Now this is a program that's made explicitly for cellular automata. It doesn't do anything else, right? And so it's very much optimized. And so it runs thousands of times faster than our homemade Python version for this particular task of cellular automata. So what do you think it's going to do? So let's speed it up a little bit more. Let's speed it up quite a bit here. We can zoom in and out with the wheel. And maybe you can predict by now what it's going to do. Uh-oh, it's made a copy. So this is really what John von Neumann was interested in. What kind of mathematical objects do we have that sort of, acted as sort of theoretical biology, right? This guy, Gregory Chatton, which we'll talk about, he talks about metabiology. This is sort of like a metabiology in the sense that this isn't chemistry. This isn't biochemistry. These aren't cellular organisms. but my gosh, what is happening here, right? This is really, really something extraordinary. Let me show you some of these other ones here. So they have these that really simulate like tapes. So here's a little machine, right? And last time Elon was saying, can we design these machines? And I think with the game of life, they've mostly been kind of discovered. But with this cellular automata, you very much can sort of, architect these things. I think it's extraordinary that anybody would be able to sort of parse this. I can't sort of just read this off the top of my head by any means at all. But I have you can look at the diagrams in von Neumann's book where they actually break it down, and you can see it's not that complicated. So they have certain pieces that will look up that it has a modular architecture, and it's no more complicated than actual digital electronics. So what's really neat about this one is it has explicit sort of a genome tape on these, and then we can run these. Let's run this one here. Oh, that's the really simple one. Hang on. There's one. They have such weird names, so I can't remember what they're. This small one, that's the one I wanted. Yeah, there it is. Okay, so here's the little machine. So this is just a pattern. And then here in this sort of tape, we could think of it as like it's DNA, right? So in human DNA, we have 4 base pairs essentially. And in this, we essentially have that same kind of thing because we have 2 sides. So we can have dark green and we have the 2 tapes, right? So we have a binary, but then we have 2 tapes. So we have a sort of a double binary code in this sense. And what's really awesome is if we run this thing, right? This pattern is going to sort of flow through this mechanism by these rules. And this thing is going to run. I'll speed this up. And what it's going to do, amazingly, is going to paint out a copy of itself and then now reconstruct its genome. This part takes a second. I'll speed this up a bit. So there's a lot of parallel processing that has to happen. But if we go over to the physics department and we ask them, what is the speed at which chemistry happens? Right? It's extraordinarily fast. I don't know if hopefully you got a chance to take a look at the David Goodsell book. I recommended from the first lecture. And he talks about that even though the molecules in your cell are randomly walking around, the speed at which they move, every molecule in your cell encounters every other molecule in your cell in about 1 second. And that kind of mixing speed is just almost unimaginable because you have about 5 million chemicals in every cell. Okay, so this thing is making copies of itself, right? This is fascinating because this is a mathematical model that can just duplicate itself. And there's an interesting idea about, what would happen if this actually happened in the real world? What would happen ultimately? And von Neumann talks about that the way probability theory works, that even though it might be very unlikely to ever have a self-replicating entity, as soon as you get one, it's then going to make copies. And then later you're going to get more copies. So we almost have to be very careful that we don't build these in real life. Right? If we were to build a self-replicating nanomachine that was able to, for instance, eat the furniture around it and build a little more copies of itself, it wouldn't have to have any goals or any ill will or any ugly intentions or anything like that, but it would just very happily gobble up the furniture until the end of time, copying itself into more of these. Say again? Exactly. So is this not life itself? Right? Is this not like, so where did the germs of life itself, did they come from an asteroid? Did they come from a, meteorite or something like this? Was it abiogenesis? Did it just spontaneously emerge in the primordial oceans? I think these are obviously still open questions. The biologists like to pretend like these are closed questions, but like DNA itself, was there sort of a simpler clay-like system before that? Okay, so there's some really fascinating constructors on here. I wanted to show you now what you can really do with this to show how universal it is. This is really fascinating. So the Gali folks went out and they actually made this set of instructions. And if we speed this up here a bit, we have a little virtual digital 3D printer that the instructions in this tape are determining what actually is going to get printed out here. Right? This is just kind of banana stuff. But we can see how this kind of works. And so we have this demo here, this construction arm. So if we go to this one, what we can do is we have these different things that we can paint on the outside, right? Or let me just go to the cell coders real quick, right? So we have these different patterns. Oops. We have the different colors here that represent the different states. And then what we can do is we can create a sort of, we can code those using this pattern. So if we set up these sort of binary looking patterns and then run them, let me slow it down and reset it. I gotta slow it down a lot. I'll put a 2-second delay. So we have up here delay. I'll put a 2-second delay. And so now they've moved over. These all turned red. Then they moved over one more. They turned orange. And now you can see they each take on the color that you've coded for, sort of on that dynamic. They sort of, it's almost like a model for morphogenesis as well. And then we can have these little contraptions here that if we restart this, they all start with a green on the end. And then depending on the shape of this, it outputs something different on the other side. So I like this as really a model for how proteins work, because those are just weird, abstract kind of designs, but yet they have these sort of functional properties based on their shape. And so this is kind of like that we take this uniform substrate, and then we put it into different shapes. The dynamic that happens here is going to control and determine what happens on the outside. So this first one's going to be a green, and they're going to become the colors just lined up like over here. And so that's how we can kind of paint these squares different colors depending on what color we need. And then this is just so extraordinary. I mean, I think just as an intellectual thing, this is pretty wild. I don't know why we don't teach this stuff in kindergarten. I think they would have a better time making sense of it than I can, because I wish I'd seen these patterns earlier. So what we can do is we can turn one of these channels on. So what we're going to do is, this is our 3D printer arm, this control arm. And what we're going to do is we're going to print one of these. So what do you want to print? Do you want to pick a color? Somebody on the remote, pick a color.
Purple.
Purple. Okay, so you want to do the dark purple? Okay, so we're going to take the pen, and then what we're going to do is we're going to take this state, the green state, this 13 with the right arrow, and we're going to connect and turn on that purple line. And since we turned on that one, since we activated that square, this branch will be activated, and hopefully this thing is going to go out and print a little purple square for us. So let's run it. Let's do a 1-second delay. Okay, there we go. We can speed up just a little bit. Okay, so there's a little square. Yeah. Again, I can imagine like the horse commentators. And they're off. We got the green square, going on the purple line, got the purple line, we got the purple. Okay, so these things are going to go and they're going to interact with each other in this cool sort of digital logic. Okay, and now we've got a purple thing going down the red. And now we've got the green coming down to match it. Okay, so it went out one square with the blue. Okay, so what happened is, it did it. It went out, the arm was there, it sort of went out one place, dropped off a little purple square, and then backed up. So let's run that again, but run a red square. So if we tell it we want to run, let's put a red square. So if we activate that one and run it, I'll speed this up. You gotta make the sound effects, right? Oh, that didn't work, did it?
It did. You printed 2.
I printed 2?
Yeah.
I got a quick question.
Yeah.
Is there any type of way to reverse engineer any of this? Like,
That's a wonderful question, right? And that's I'm honestly shocked in the sense, because I've been looking at this Golly program for a few years now, and I hadn't quite seen some of these newer with this C arm and stuff. I hadn't seen this demo before. And so that suggests to me that people are very actively working on this field, but yet I couldn't find anywhere about like, where's the instruction manual, so to speak, about how you would design these, right? So I found von Neumann's original thing, and it's extraordinary. I'm trying to find out, who came up with the C-arm design itself. I found the original paper, but it doesn't have, quite enough of a detail. So in terms of like what you'd want it to get it to do, that's what I was, I kind of challenging, myself and then the class. I would love for this to print out like MPCR or something like that. It would be so fun. And so I would love to I was thinking about this morning, could we make a compiler that if you told it what you wanted to print out, we should be able to make another computer program that just very quickly says, like, we should be able to draw in Microsoft Paint. I'm sorry. We should be able to draw this in Microsoft Paint and then write another Python program that determines what this pattern would have to be to get that thing printed out. And I don't think that's that complicated based on what we have with this ARM here. I haven't seen it. So that's the thing.
I have a strange suspicion that it might be impossible, just like almost halting problems style, because you have to run it in order to get the output. I mean, I'm sure there's like a taxonomy of like or some cataloging of this is the family of these, and there might be some similarity.
Yeah, there actually is sort of like, if we go to the wire world, it's sort of funny because there are sort of a couple sort of principles, right? So here's like doing logic gates. And so for little stuff, I can imagine you could kind of code these by hand, or you could kind of, brute force them in a sense. You could even probably try to find them.
You kind of Lego them somehow. Right, exactly. The people.
Yeah. So here's some principles. And then I think what they did is they took principles that are known from, like, for this prime number calculator. This is simulating something that's already known about electronics, like 8-bit registers. So what's really fascinating, but somebody has, and again, I would love to figure out how they did this essentially, but they've converted electronic logic into this other form. But what I'm missing is sort of the intermediate, right? Did they just sit down with like 12 pots of coffee and just like, draw this thing out? Or is there some other intermediate representation that helps them sort of map these two domains? It's a lot like the Andrew Coward thing. We know how this works. We know how whole circuits work. We know how they work with electricity, but actually mapping it to these, this different kind of logic, I think is fascinating. And it's not clear yet how they're doing it. There was that other one that we looked at with this super, that was super kind of fun. And this one it's a lot like the von Neumann in that we have all these different states, but there's like so much going on here. They're like little firecrackers, and some of them turn on and off, and so on, right? Like that one sets that one like dominoes, and like this one will eat that pattern, but not the other stuff, and this other one that got turned on but then off, and all this. All right, this one's gone soon, and then it has the other pieces that stay on. So I can imagine you could build, logical things. You could definitely make a sort of a principled approach to this stuff, right? You could start building primitives, right? It says in other words, we know we have if and else out of here by doing the and the not and all that kind of stuff. So theoretically, we could just build up other kinds of algorithms. I think this is a very open area of research. I think there's definitely a lot of work to be done on this. I think even just in these John von Neumanns, I'm very excited about using deep learning. Like, could we use an LSTM to design these, right? Could we use a GAN, a picture GAN, to generate more novel circuits that run like this? Okay, so that's the Golly. Did anybody remote find anyone of interest that we haven't pulled up that they want to mention or screen share? Say again? Termites? Okay, so there's which right here, termites? Which one in particular?
I don't remember what it's called. It was the one that simulates Langston's Zan.
Okay, so here's one.
I like Langston's Zan.
Let's let that one run. So there's this this other model right here called Langston's ant, and this one's a universal Turing machine. So we're going to look at Turing machines in the next couple of weeks. And so this one is like a little ant, and it runs around. And let's see, at a white square, it'll turn 90 degrees clockwise. Somebody's got their mics they need to mute. So if you hit a white square, you turn 90 degrees, you flip the color of the square, and you move one unit forward, right? So you could do this yourself. We have tiles on the floor here. We could kind of simulate that. There was a suggestion that we go have class outside one day, and then we can actually simulate these things outside. That'd be kind of fun. I think it's good to actually embody these algorithms and like pretend like you are the algorithm. There's a famous story that one of the developers of these languages, they set out to teach children how to draw a circle using these programming languages. And so they ask the kindergartners, and they say, well, how do you make a circle? And they have the kindergarten, they say, close your eyes and make a circle with your body. And so the kindergartners sort of close their eyes, and you go a little bit, you turn a little bit. You go a little bit, you turn a little bit. And these kids are actually able, these little, like sort of first graders or so, they're able to program and make a circle using this computer language. Well, then they go to middle schoolers, and they ask the middle schoolers, say, can you program a circle? Well, the middle schoolers have already learned this stuff about radius and all of this kind of stuff. And so they figure out how to do it too, because in their mind, what a circle is you start at the origin, you go out a little bit, you make a dot, and then you go back, and then you turn a little bit, you go out, and you go back, and you make a dot. And so it's not quite as efficient, but they're able to make the dots this way. And then when they get to the high school students, the problem is the high school students they know things like algebra. And unfortunately, they can't solve the problem because they have too much sort of mental baggage in the way about formulas and algebra and all this stuff, and they've forgotten, how to actually make a circle with your body. And so I think it's important to embody these things, like pretend to be an ant. Right? Your friends will think you're crazy, but that's part of the fun of being a complex systems scientist. Okay, so that's the Langston's ant and so this one's made out of this termites rule. So this is a slightly different rule here. Do they have the termites rule as its own rule? Let's see.
Wait, I'm confused. So does he eventually make a circle?
No, not in this case. I'm sorry. I was just telling an unrelated story about how important it is to kind of think of yourself as the agent. In general, when you're designing these algorithms, you want to kind of pretend, all right, I'm a tree in a forest. I have a neighbor here, a neighbor there, a neighbor there. I can do the following, right? To kind of simulate, to zoom in and pretend like you are the ant and look and see like what those rules would be. Oh, it is termite with the
It is.
yeah. So I didn't spell it wrong. I spelled it this goofy way. Oh, I get it. Turing machine. Oh, I never got that. Termites. Okay, so this is a two-state, two-color termite. As Misha's saying, it's a joke of Turing machine. And then so we can see this sort of chaotic, irregular behavior. So, all this stuff kind of emerged in the 80s when people finally had computers that could do graphics, and they started to run these equations, and they said, wait a minute, this stuff is really counterintuitive. No one would expect you to get these particular patterns based on these very, very simple kind of rules.
If you can find, there's a snowflake one in, I don't remember whose rule it was.
So typically, I think the naive thought would be in science is to get a complicated pattern, you had to have a complicated process. To get a complex pattern, you have to have a complex process. And I think the whole point here that we're seeing is that to really get to very sophisticated patterns, you do not necessarily need sophisticated rules. To get very sort of unpredictable behavior, there's no coin in here, there's no dice, there's no random numbers. There's no sort of, weirdness injected from the outside. The error is sort of intrinsically in the system. Did anybody else from online find any that they were interested? They thought were interesting?
There's one in my.
I just have a question about the rules.
Yeah.
Does it always have to involve a neighbor, or is there a way to calculate, like if there's a certain distance to something and then set up the rules that way? Would it still produce this type of
Yes,
pattern?
great question. There's another one, like continuous life. Do they have that one in here, Misha, or is that
I don't
in?
think they have that in there.
That's in the other program. Okay, so that's a great question. That allows us to switch over to the other program. Yeah. So, like, what if you have like a fuzzy definition of neighbor, right? This is like sort of a very rigid, like you're in a square or not. What if we have like a softer kind of reality? And so there's another program for that. So let me pull that up. And that one is called Golly. No, not Golly. No, Ready. Oh, they deleted it because I downloaded. That's funny because it. Okay, so let's just re-download it. So if we type in Ready Reaction Diffusion, it's from the same group. It's called Golly Gang, is their GitHub. And so we can download this other one. I'll just take a second here. And this is another really awesome program that's going to allow us to do the continuous versions of this. So let's take a preview of that. And then next time we're going to code those up ourselves. So let me extract this to the desktop here. So this is going to be a slightly different version, no longer discrete mathematics, but a sort of continuous mathematics. Okay, so there we go. Let's open that up. There we go. Ready. We're going to tell Windows that's okay. We're going to run it anyway. Okay, so this is very much in the same flavor as the other program, except now we have sort of a 3D world that we can move around in, and we're going to do some different equations here. So one of these is this gray Scott, and so we're going to simulate this next time in our Python. And so if we just click on one of these and run it, we're going to get this amazing simulation. How do I reset this one? I forget now. Let me slow that, see if I can slow that down here. So we get this sort of amazing, like kind of like a bacterial, doubling kind of simulation. And this is with continuous equations, differential equations. And we're going to see how sort of mind-numbingly simple this Python is. And so from a mathematical point of view, this is kind of really difficult to get the solutions of these. But when we use our computing machine, these are really simple. It's really simple. It's been sort of maybe jokingly said that, Newton invented the calculus only because he didn't have a calculating machine. In his notes, they have where he did sort of by hand the equivalent of using a computer and making small little steps and actually just simulating the math himself. And then after a few pages of that, he was kind of like, oh, this takes too long. And he invented the calculus to get around that problem. Right? So had he had a computing machine in Python, he probably would have never invented the calculus. Okay, so this is the Gray Scott. There's a tremendous number of really interesting ones that we're going to look at. We're going to simulate Gray Scott. We're also going to simulate the Fitsun Nagomo equation. And so this is just really extraordinary. When I got this programmed in Python from scratch, I was just so excited because I had seen this run in this program for years. And I was just really fascinated. So this is like the patterns you see on fish if you go down snorkeling or scuba diving or something. And you'll see on the coral reef. Also looks kind of like the brain structure. Turing largely developed this field of morphogenesis, and he was interested in how the brain actually developed. He wanted to get intelligent machinery, and he thought, well, the shape of our brain is important, and it develops over time, so maybe it might be easier, right? Remember, his original idea said, rather than creating an intelligent adult, let's make a learning machine. Let's make a baby and have it learn as it grows. And then he thought, well, let's even easier than that. Let's not even make a baby. Let's make an egg, essentially, something that can grow and develop into the shape that then would be able to learn, right? So it's sort of like a really cool way of getting at this kind of stuff. There's some really interesting ones, Ginsburg-Landau. This has to do with superconductivity, so there's some really great physics here that you can look at. And these kind of make like really cool little mushroom cloud-like type shapes, which is really kind of wacky. Okay, so the question was, what about life and having one? So there's one called smooth life, which is like what you were asking about. And this one is sort of a generalized version of the rules. And basically you have, you live or die based on the floating point numbers rather than yes or no choices. And so you have chances. And what's really interesting is you get these very different behaviors emerge. And so what's stable and what shapes and sort of what forms you get are very different. And so they're not all these they don't look like the 80s video game characters anymore. What was that game called? We just shoot Space Invaders. Yeah, it always looks like Space Invaders to me. This looks really kind of wacky and kind of a little organic. Yeah, it also supports these gliders, right? So you get these sort of mobile units. So again, it's like the emergence. It seems like there's this entity that's moving along, but really it's just, again, it's all in parallel. So here we can see Turing's 1952. He was trying to figure out the spots on a cheetah, that sort of a thing. And so there we have a math model of that we can run. We can add some noise to that. Let's see what's some others that we can run in here. Here's some really fun stuff about non-rectangular arrays. So we can make like a glider and a loop in like a world like this. And so we get little creatures kind of emerging out of that kind of world. So I'm going to post this link. Be sure, again, you got to run this stuff for yourself, right? One is just, don't let me have all the fun here. Someone was asking earlier in 3D, right? So there's sort of a 3D, a nice 3D version. So there's sort of some 3D automata, right? So we could very easily probably do the 3D forest fire in here. Here's a really fun one that you can do. This can really change the boundary conditions, right? And so if you're an ant on a donut, the world is two-dimensional, but you can never leave. And we can actually run Game of Life on that world with this so-called, periodic boundary conditions. That's what they call it. Now there's another one that'll do it with a rabbit. Let me see, where is that one? Fitsun, Nagomo. I thought that was Turing. They keep adding more. This is really awesome. Every time I download this program, there's more. There's one of these, they actually run the equation on like a surface, an arbitrary surface. And so this program is very powerful. We don't have to just run it on a square. We can run it on like an arbitrary pattern. There we go. There it is. All right, so there we go. We can add an arbitrary mesh, right? So you could theoretically 3D scan yourself and be like, what if I were a cheetah, where would my spots be? Something like that. And so if this bunny rabbit were a tropical fish or something, that's where its spots would end up. Oh, here's the lion. Here we go. All right, so there we have the 3D mesh, and now we can run this on there. Right, so it's important to remember, 100 years ago, science didn't have a clue how, zebras get their stripes or how lions get their patterns, right? There's okay to say, well, it's in the DNA. Well, no, every cell gets the exact same copy of the DNA. So how does the cell know whether or not which proteins or what to actually express? So I think this is just like an extraordinary branch of math that, because it runs on a computer, mathematicians ignore it. Because it's made out of math, computer scientists ignore it. Because it's both of those, scientists ignore it. And I think there's an incredible opportunity, to put this stuff into science. Right? Some of these things, like you hear, see, in 1993, they couldn't dream of running these things in 1993. And so now we get this extraordinary kind of crystal growth and so on. So we're about out of time for today. So this program is called Ready. You can find it online. I'll post the link, Reaction to Fusion. Be sure to go through there and see what you can find. Some of these are brand new. It's neat to see some of these old ones, but it's also see that people are still working on these fields here. They're 2020. These are still active fields. All right, thank you for your time and attention. If there's any questions, we can take them now. If not, you can send them to me by email. And if not, we'll have a great weekend, and I'll see you on Tuesday. Any questions on the remote?
Yeah, there's one question from me.
Please.
I was looking for the recorded videos before. I couldn't find them anywhere.
Elon, are you still connected?
Yeah, I just sent a little bit before this class. I sent you the link so that you can just post it on Canvas, because I realized I can't post. I guess I could post on your Canvas. I just realized I could. Maybe that's even simpler.
Well, where in Canvas are you posting them? Cisco WebEx, the media catalog.
I can post on the classes Canvas site, and it's just a WebEx link. So
yeah, so just put them in the announcement section. It'll be good.
Yep.
Yeah, I was just searching around, couldn't find them, and I wondered.
They have not been findable. So
right.
they will be
Gotcha.
as it say.
Oh, and a question for Mr. Hahn.
Please.
I was looking over the von Neumann turning machine, and earlier you showed us an example of the self-replicating one.
Yeah.
And I was looking at a paper that he was writing before, and he was basically talking about adding mutations in the tape and how it carries over to each iteration afterwards.
Yeah, with the little flower.
Yeah, that's the exact one.
That's extraordinary. Yeah, would you want to remind me, and we can talk about that on Tuesday?
Yeah, I was gonna ask you about that specific topic, if you can like expand on it.
Yeah, let's talk about that on Tuesday, because I think that's a tremendous direction.
All right, thank you. That's it.
All right, thank you.
Okay, I'm ending the recording.
All right, thank you, everybody. We'll see you in the next session.